Can you see the screen?
Yeah. Yes, sir.
Okay. So we had a power cut on UCC. Okay, shall we continue? So, so I'll just so the values look like these, right? So if you calculate, so this, suppose if you are selecting this column, right? So A and G, so it's a mismatch, right? So that is -2, right? Then G with this gap, right? So that's mean -1. Then this A with this gap, and again -1. So basically we have -4 here, right? Then so I think okay. Then if you get some column like this, right? So T with T, so it's a match. So we have 3. Then T with G, right? So it's a mismatch, right? So -2. Then again this T with this G, so again it's -2, right? So basically -1, right? Then so these are same. So that's mean T with T, this T with T, and this T with T. So finally get 9. Then suppose some kind of this, right? So A with A, so that's 3. Then A with this gap, so that is -2. So then you sorry, -1, right? Then again this A with this gap, -1, right? Finally you get 1, right? If you have any questions, you can ask on this. I think it's very straightforward, right? So up to now, we discuss how we get this scoring, right? Sum of pair scoring thing, right? So then, so this sum of pair thing is not a perfect scoring system, right? So suppose you have something like this, right? So we define our values as if we have identical pairs, you get 1, otherwise you get 0, right? So you can see that. So these are same sequences, right? Let's suppose this is sequence A, right? So these are different sequences, right? If you align these all these 6 together, right? So these value, if you calculate the value, right? So that value is dominated by these same sequences, right? Right. Even though this alignment is not optimal one, so even though you get a higher value, right? So that's why I mentioned at the beginning, right? So if you have in your alignment, if you have same sequences from identical sequences, right? So those are dominate in the value, right? So we go in here, we try to get the optimal alignment, right? So you should align these these are other sequences also, right? You have to align those things in some kind of a optimal way, right? So in here you can give some gap or something like, if you calculate the value, right? So you can give a gap and put y thing here, or you can do such things, right? So, so basically, so this SP is not a perfect scoring system, right? So it is basically easily biased towards if you have same family, so overrepresented in the your input sequences. So it biased towards those sequences, right? For that you can overcome that disadvantages using some weights, right? In your case, we are not going to discuss those weighted sum of pairs, right? You just keep in mind if you have to overcome this kind of disadvantages, right? So you can introduce weights, right? So you can introduce if you have some kind of uh, this kind of alignment, right? So you can give some weight for that one, so like 0.1 or something like that, right? So this value will be we can reduce this value, right? We can get a smaller value for that one, right? So then these are more dependent on these values, right? Like that we can introduce weights, right? In like other approaches, like you can have some entropy based one, right? So in your case, we are not discussing those things, right? So are you okay up to this point? So I hope you can get a calculation like this. You can do a calculation like this and get you can compare several alignments, right? Based on the value. Then so this sum of pair scoring system is a standard one, right? So it's a can you guys hear me?
Yes.
Okay. So it's a basically a column column by column cost rate function, right? So so for that to get some values, we use that as I said before, we use a substitution matrix. So that could be a Blossom or PAM, right? So there are several substitution matrices, right? Then so we try to maximize the total alignment score, right? By maximizing the each column value, right? So we try to get the total maximum value based on uh, by maximizing the each column value, right? So we try to get the maximum value for each column, right? So if you get the maximum value for each column, so simply you get the maximum value for your whole alignment, right? Then okay, so that's it. Then we going to do this multiple alignment, right? Now you have a scoring mechanism, right? Suppose you have some kind of alignment. Suppose you did some dynamic program, whatever thing, then you get suppose you get some alignment, right? Now you have a scoring mechanism, right? You can use sum of pair to mechanism to evaluate those alignments, right? Then we going to discuss how we going to align these sequences, right? So we discussed one thing is a dynamic programming, right? We already discussed that one. Then we have in this lecture we have progressive, iterative, and block-based alignment, right? So these are the alignment methods. Then that sum of pair is a scoring method, right? So after you align several sequences, you can use the sum of pair or whatever scoring mechanism to evaluate those alignments. So in progressive alignment, it's some kind of a greedy approach, right? So it has several steps, right? So basically, we use this progressive alignment to for close sequences, not for distant sequences. That means close related sequences, basically, right? So we introduce gaps, right? Then if we introduce gaps at so this is some kind of iterating thing, right? So first you introduce some gaps, so those gaps are there for all the time, right? So you can't remove those gaps, right? So so it works like this, right? So first you get the pairwise distance scores, right? So you calculate in the you do the pairwise alignment, right? Then you get some kind of a value, right? So we can call that distance, right? So that's mean how similar those pairs, right? So suppose you have three sequences, right? So you first you conduct this pairwise alignment, right? Then you get how similar these pairs are, right? then then you generate guide tree. It's like a phylogenetic tree, right? So that's based on how those these sequences are similar, right? So I'll show you an example, then that will be fine, right? Then finally we align the all the sequences based on that guide tree, right? So so this cluster uh, W is one mechanism of progressive alignment, right? So it has a progressive approach, but it owns several uh, mechanisms, right? So as first, so basically you have to construct the pairwise alignment, right? So you know how to construct the pairwise alignment, right? Then based on that pairwise alignment, you build a guide tree. Then you based on that guide tree, so so based on that guide tree, you're going to progressively, that means sequentially aligning one by one these sequences, right? So I'll show you example, right? Suppose you have this kind of so you have several v1 v2 v3 v4 sequences, right? So first you align these sequences like pairwise, right? So basically you uh, align these things pairwise, and you get some we call this simulated matrix, right? So this thing shows how similar these matrices are. So these sequences are, right? If you consider this v2 with v1, so it has some kind of a 0.17 value, right? So it's a very low value. Then if you consider this v3 versus this v1, so it has some kind of a 0.87, right? Like that. So this show basically how similar these sequences are, right? So based on this value, we can then generate our phylogenetic tree, right? So you do some pairwise alignment, right? Then generate these similarity values, right? We call these similarity matrix. Based on this similarity matrix, we build some kind of a tree, right? Like that, we build some kind of a tree, right? Then for this scoring mechanism, we for to align to get some these values, we use basically these substitution matrices, this blossom mop and whatever thing, right? So that's so these things are same as pairwise alignment, right? So you done these things previous lectures, right? I think Miss Amali covered these things, right? So these things are covered in the previous lectures. So these are same as the pairwise alignment, right? Basically, you generate some matrix, right? So that's the different, right? You get some values. Then, right, based on these values, so you create a guide tree, right? Guide tree is some kind of, so this is the guide tree. So it based on this similarity matrix, right? Suppose so you go one by one. So v2 with v1, so you have smaller value. So the biggest value is v3 with v1, right? So we put v3 with v3 and v1 closely, right? It has some place like this. Then we consider, so the next value v4 with v3, right? So v4 with v3, right? So it has some kind of this 0.62 value. So it should be some kind of this place, right? We have a different algorithm for this neighbor joining thing, right? So I'm just give some abstract idea, right? Like that, we generate this guide tree, right? So this guide tree is generated based on this similarity matrix, right? Are you guys okay up to now? So is it
Yes.
okay? Okay then. Right. So so as I said before, we have a different algorithm called this cluster W. So in cluster W, we simply use this neighbor joining method to create this phylogenetic tree, right? So this guide tree basically reflects some kind of evolutionary relations, right? It reflects some rough relations about how the evolution begins, right? So if we have some values, so if we have two sequences like these, right, we can tell that. So the separating point is like this, right? So I think you done that that paralogous homologous thing, right? There are several words. Actually, I can't remember those things, right? So we can have some. So we can have same ancestors, right? So we can have same ancestors like that. So those things will cover. I think there are one lecture on phylogenetic tree, right? So I think those things will cover on that lecture, right? Basically, you have to keep in mind how the flow works, right? So basically, you made the similarity matrix. Based on that, you made the guide tree, right? Right, based on these values, so you place those sequences at the correct place, right? Then right, so if you do the progressive alignment, right? So the third step is progressive alignment, right? Third step is progressive alignment. In here, we do we aligning these those sequences based on that tree, right? So first, so V1 and V3 is the closest one, right? So we first align V1 with V3, right? So we call this V13, right? 1 comma 3, right? So we can write here V13. We can remove this one, right? We can write V13, right? Then so the V4 is the next closest one. Then we align this V13 with this V4, right? So we get, so it returning some sequence like this, right? Then the finally, so V2 is the uh, most far away thing. Then so we align V134 with this V2, right? So after that we get some kind of a V1234, right? So basically, so first you align V1 with V3, right? For that alignment, suppose you have set of values, right? So you can introduce some gaps, right? So I need some kind of gap here, right? Like that, you suppose you have some A, C, T, G, right? Suppose A, C, T, G, right? So I, at the first alignment, I put a gap here, right? So I put that one by my hand, right? Then so this is C. Then suppose you have some A, C, this is G, this also G, something like that, right? So we can have either, we make it C, right? Right? To align this G with G, I'll put a gap here and shift this G into this place, right? So I can align this G with this G, right? Like that, we can introduce gaps, right? Then suppose now you have the final alignment, right? So V13, so this is the final alignment, right? So then you align that thing with this V4, right? When we try to align with V4, we already have a gap here, right? So I put a gap for V1 in this place. So that gap is there, right? When we aligning with V4, right? So suppose you have something like A, T, G, C, something like that, right? Now, if you want to, uh, get this G into this place, right? Suppose you want to get this G into this place, you can't remove this gap, right? So if you introduce a gap at alignment, so that's permanent, right? So that's the basic drawback on this progressive alignment, right? If you put a gap at the very initiate point, right? Like aligning B1 with B3, right? You put a gap, right? At the end, suppose now you have, so that gap is now working at like so it working the other way, right? So it basically reducing the score value, right? Like that. But even though you can't remove that gap, right? So just one, so that's the one drawback on this progressive alignment, right? So you have to go one by one. If you take a decision, so that will last long, right? So you have to, so if it's a good decision, that's fine, right? If you made a mistake, so that will propagate, right? So that will affect the whole the alignment, right? Right? Okay. So like this you can, so this is I want to mention, if you insert a gap as necessary, so once a gap, so that will last long, you can't remove that those gaps, right? If you introduce one gap, so that will therefore all the time, right? So you go one by one. So first you, suppose you first align these two, then these three, these four, like that. You add in the most similar sequences to your existing one, right? So these are, suppose this is the most similar two sequences, then you add the next most similar sequence to these two, right? Like that you keep aligning, right? That's why we call it progressive, right? So we have some kind of sequential adding process, right?
So
Yeah.
මේ එතන පළවෙනි පාර ගැප්ස් දාද්දී ඉන්සර්ට් ගැප්ස් as necessary ගහම අපි එතනියා හිතලා වගේද නැත්නම් මොකක් හරි අපි follow
ඒ කියන්නේ
කරන්න
අපි try කරන්නේ ඒ time එකේ තියෙන problem එක optimal කරන්නනේ. හරිද? එතකොට ඒ gap එක as necessary කියන්නේ අපි මේ try කරන්නේ gap එක introduce කරලා මේ එතන alignment එකේ තියෙන උපරිම score එක ගන්න. අපි එහෙම try කරාට but at the end, so that will affect the whole alignment, right? So that's the basic idea. Then so this is the same thing, right? So you can have several alignments, right? You can put this, if you have two set of alignments, right? Then you can either have so this is this, so you can either align like this, then else you can have some, introduce some gaps and align like this. Like this you can introduce as you want, right, to increase the value, right? But if you introduce a gap, so that's, so if once a gap, so it will always a gap, right? You can remove at the other iterations, right? Other sequential, if you adding other sequences, you can remove at that point, right? So that's the progressive alignment. So there are, these are the limitation on this one, right? So as I said before, so basically initial decisions will affect the whole alignment, right? So that will be very far from the optimal solution, right? Then this is depend on the guide tree, right? So you keep adding these sequences based on this guide tree, right? That's another drawback, right? So I'll give an example, right? Suppose you have kind of this thing, right? So in here you have ACG, ATTG, AGAG, ACTG, ACAG, right? So now you add that now you generated this guide tree, right? Now you're trying to align based on that guide tree. You done that similarity matrices and you made this guide tree, right? Then so first you can align these two, right? Because these two are most closer things. Then this adding this to this, right? Now you finally have kind of this alignment from one hand, right? If you consider other hand, right, you can either, so this has only three elements, no? So you have to introduce some kind of a one gap, right? So you can have several alignments, right? You can have like this or this, right? If you go for this one, so what will be the outcome? If you select a gap CG, ATTG with, then so if you final this one in the left side, then you try to align with these two, right? So what will be the value? What will be the outcome? So is it a good alignment, right? So you can G saw here, right? Then CT, then gap T A, right? So if you consider the other alignment, you can have several alignments, no? If you consider this one, so it has A here, G here, so these are same. Then CT, right? So you already have two C's here, right? Then so I think the best one should be this one, right? So at the initial point, you can't decide what will be the correct alignment, right? So that's the drawback I mentioned, right? So if you go for the correct one, that's okay. If you select the wrong one, so that will be very that will be, your solution will be very far from the optimal one. Right? Are you okay up to now?
Yes, sir.
Right. So, okay, so the answer is the second one will be probably the correct answer, right? So the our algorithm will look like this, right? Right. First, you should have right. You have set of sequences here, right? Then you align this with, you done the pairwise alignment and construct this similarity or distant matrix, right? So now we have this value. If it's a distant matrix, right? So you should get the I think lowest value, right? If you have the similarity matrix that show how these sequences are similar. So if you have a similarity matrix, so you should go for the highest value. If you have a distant matrix, so that's basically telling, so these sequences are very far from each other, right? Like that. So at that point you should go for the lowest value, right? If you see, so AB you have 11, right? Then CD you have 9, right? So AB are coupled in here, CD are coupled in here, right? So E is single forever because you have a higher distant matrix, right? So it's same as the your personal life, right? Then suppose you have this distant matrix, right? Then you construct this guide tree. Based on these values, you construct this one. So A, B are closer, then C, D, then E, right? Then you align these things based on this neighbor joining algorithm, or whatever there should be algorithm, right? So we are not discussing those things in here, right? So at first you aligning A, B here, you have A, B here, then C, D here, right? Then at next point, right? Now you have A, B, and C, D alignments, right? Now we have two alignments. So this is, suppose this is A, B, this is C, D, right? So, and the previous slide, you have one alignment remaining. So that is E, right? So you should align in this A, B together and C, D together with that E, right? Right? Now we have now you aligning CD and AB together. Now we have CD AB. Now you align that whole CD AB thing with this sequence E, right? Finally, you have the final completing alignment, right? So that's how the algorithm works, right? So is it okay up to now? So is it okay?
Yes, sir.
Okay. Then so I'll give a small example, right? Like this. So if you are not familiar with the DNA and those things, so you can have some kind of this text, right? So Garfield, the last fat cat, right? So that is so we take it as sequence A. Then we have another one, sequence B, Garfield, the fast cat, right? So in here it is fat, in here it is fast, right? So by looking at these two, so we can so these two are like similar ones, right? So you should aligning AB first, right? You can introduce gaps here, right? Then you can have some other gaps, right? Like that. So the sequence is, so you can see by going in this way, so that these sequences are very dissimilar, right? So in here you have Garfield, the very fast cat, right? So these things are mutated, right? So at the first point, so the Garfield is the last. So it is we know it's a fat cat, but after it uh, this string is mutated, so it becomes fast, then very fast like that. So it keeps changing, right? So it is same in the DNAs, right? So that's why we want to aligning these sequences and check how similar those things are, right? So that's the whole purpose of this multiple sequence alignment, right? So I hope you are okay up to this point. Then we're going to discuss this cluster W algorithm, cluster W method actually, right? So this cluster W is the most widely used one, right? Then so it is one progressive method, right? In here, so the main difference is, so you do the pairwise alignment based on this dynamic approach, right? You based on the dynamic approach, you do the pairwise alignment, right? Then you use this phylogenetic tree to produce this as a guide tree, and you use a neighbor joining algorithm to join those things, right? Then you the third step is same as the progressive one. So you basically sequentially keep adding these sequences, right? So it more like same as the progressive one, only some difference, right? You use dynamic programming, and this we mentioned this guide tree as a phylogenetic tree in this cluster W, and you use a neighbor joining algorithm to join those sequences, right? So base same as the progressive one. So if you have gaps, so those gaps are fixed, right? So those gaps are cannot be deleted, right? You can only add those gaps. So the problem is, so it has a same as drawbacks as the progressive one. So it has a dependency based on the initial pairwise sequence alignment, right? If you take a bad decision, that will affect your whole sequence alignment, right? Then so it will propagating errors from initial alignment, as I said before, on the progressive one, right? So this cluster W will look like this, right? In here you have a suppose, so you have set of sequences here, right? Then you should you do the dynamic programming, pairwise dynamic programming, right? Then generate this similarity matrix, right? After that, based on this similarity matrix, you generate this phylogenetic tree, right? After that, so you have this phylogenetic tree. So based on that, you generate the final sequence, final alignment, right? So A is the set of sequences. Then you pairwise do the dynamic programming. Then you get this similarity matrix. Then you generate this phylogenetic tree based on the neighbor joining algorithm. Then you sequentially align these uh, sequences based on this phylogenetic tree, right? So as I said before, so the as a scoring mechanism, you can use sum of pair or whatever you want, right? So you can see the how what is the usage of sum of pair, right? So you done the alignment, right? Now you have some sort of alignment here. Then you use some kind of uh, that scoring mechanism to get an final value, right? Right? Is it okay? So it same as the progressive one, only some changes, this dynamic programming and this neighbor joining algorithm, right? Is it okay?
Yes, sir.
Okay then. So then the next one is iterative algorithm, right? Right. So the next one is iterative algorithm. So so it's same as the progressive one. Okay. Right. So so we repeatedly modifying the existing suboptimal solution, right? So we keep iteratively optimize these suboptimal solutions, right? So we started from a low quality alignment, but we gradually improves it, right? So not like the progressive one, right? Or if the progressive one, if you put a gap or something, we did some bad decision, so that will last long. So in here we try to, if you can have a low quality alignment, but you can gradually improve that one, right? So we iteratively try to get the optimal alignment, right? So we do that thing until no more improvements. So if you final the improve alignment score, then you go for the next iteration, right? So for each each sub problems, you make you improve that one, right? Gradually improve the solution, right? So it kind of a greedy approach, but it has some progressive strategies, right? So also this thing in some point they mentioned that this thing not guaranteed the final give us some optimal alignment, right? So in here we not discussing about this method. There are just as your information you can have this we have muscle, this MAFT, PRRP, like that. We have several uh, algorithms based on this iterative alignment, right? For the progressive one, we only discuss the cluster W, right? So, so if you consider this iterative approach, right? So basically, we try to reduce in the errors, right? So in the progressive one, you can't, if you did some change, right? You can't alter that one, right? But in here, we can came to that point and change that thing, right? That means we can give some, we can optimize that thing, right? Then, so it's the same thing, right? So the progressive alignment, it dependent on high quality initial alignment, right? If you have a bad alignment at the very initiate ages, right? So that will affect your final alignment, right? So, but in the, as I said before, so we can get rid of that thing in iterative alignment, right? So, okay, one thing, this so that in progressive alignment, we it has a we improves our efficiency at the cost of the accuracy, right? We can we can have the very higher efficiency, right, in progressive one, but we can't guaranteed about the accuracy, right? So in the iterative algorithm, so we can tell that it has a better accuracy than the progressive one, right? Then so these things are you already mentioned, right? So the algorithm will look like this, right? So you have set of sequences, you made the guide tree, right? Then you can have either weights or something like that. so it has an inner iteration. So in the inner iteration, you dynamically align these things and try to get the optimal alignment for this sub problem, right? So if you done the iteration, so you have finally have the most optimum sub problem solution, right? Then you go for the outer iteration, right? Then so if you have this coins converge, then you can go for the outer iteration, right? So just keep in mind just a abstract idea, right? So basically you can focus on the progressive one, since we discussed that progressive alignment around 1:30 around 1 hour, right? So so just keep in mind this. There are other approaches like iterative approach like that, right? So I think we are at the end of our lecture today, right? So I'll discuss this block-based alignment in the next day. So I think that's it. If you have any questions, you can ask. So the next 2 weeks, we going to, in the next day, I'll discuss this block-based algorithm is HMM. Then, and the final week, we'll do some details on the neural networks, right? So this is some very, as I said in the previous lecture. So this is a very this subject has a higher GPA, right? So that means probably you can get a higher grade, right? So try to get the most out of that thing, right? So so I'll upload the slides, right? I dropped some things like these in the sum of pair scoring method. You can have these entropy based scores, right? So I dropped those things actually. So I think that won't be very useful for you guys, right? So just give the focus on this progressive alignment and this sum of pair, right? So probably you will have a question on that thing, right? One question actually from I think there will be one question from my part, right? Multiple sequence alignment, HMM, and the neural networks, right? The neural networks we just have 1 week. No, we just get some abstract idea, right? So I hope you can you get something out of this lecture, right? If you have any questions, you can ask. So if you can understand the flow, that will help you to understand the whole subject, right? So first you have to know the why I learn those things, right? So if you studying this like sum of pairs, so there may be some point that will be used, right? So sum of pair will be we are using basically for evaluate the alignments, right? Like that. So we have set of methods for aligning the sequences, and we have some set of methods for give some score for those alignments, right? Like that, you have to make some story, right? I'll try to build that story, but if I fail, so you can go through my lecture slides, right? Then you can get an idea. So that's pretty much it. So we are at 2:30, right? If you have any questions, you can ask. Then else we can end today's lecture. So I think you have this Friday you have that phylogenetic tree, and the next week 29th I think you have that quiz, right? Again you will have some quiz from my side also. So we'll see. Okay, then shall we stop the session? So I think you don't have any questions. Okay, then thank you very much. So I'll stop the session. I'll upload the slides as well as the videos. I upload for both the IS and the CS guys, right? You can check the VLE. Right. Thank you.